Okay, well, hello and welcome to this online lecture on in vivo dosimetry. And this is day, 3 of many of home working in pyjamas. I've not changed for days. Son's at home. He's in here.
Yeah.
There we go.
Yeah.
Home working.
Yeah.
I assume that he's actually doing some work.
Yeah.
I'm sure he is. Here we go. So yeah, here we go. We're we have toilet rolls. There's a black market economy here. You can see down there, enough for quite a while. But we've had those in there for ages. We've not been stopped buying. Anyway, yes, this is the real world, and let's crack on with something important. Okay, hello everyone. Welcome to this online lecture on in vivo dosimetry, which is verifying the dose that we deliver to patients during their radiotherapy. We know that we verify geometric accuracy. Might be considered equally important to verify the dose that we're delivering to. So in this short, punchy lecture, I'll go through what in vivo dosimetry is, the ways in which we can do it, the merits and limitations of them, and then I'll follow that up with a short Q&A session with another Zoom webinar, and then there'll be an online test that you can use to self-assess. And what you can see on the background to this slide are a number of documents that recommend the use of in vivo dosimetry, and we'll come back to some of these as we go on, but these are ones that you might want to refer to. So World Health Organization, Royal College of Radiologists all recommend that there should be some form of dosimetric verification during the delivery of radiotherapy. So why do we need to do it? Well, the first thing that we need to be absolutely clear on is that dosimetric errors can and do occur in the planning and treatment of patients. We know that in an ideal world, the dose that we plan is the dose that should be delivered to patients. But what we'll see on the next slide is that there's lots of stages in the radiotherapy pathway where these errors can occur. And so we need to ensure that these aren't at a point that they might begin to significantly impact on tumour control probability or normal tissue complication probability. As I've already mentioned, it's actually a recommendation by lots of bodies. ICRU in report 24, I think it was, as long ago as 1976, recommended that in vivo dosimetry should be a routine part of radiotherapy. World Health Organization in the late 1980s, as a result of some serious systematic dose errors that occurred in the UK, in both Exeter and Stoke, they recommended that in vivo dosimetry should be a routine part of radiotherapy. Now, also the Royal College of Radiologists recommend the use of in vivo dosimetry radiation checks should be made routine. Now, you will know from your own experiences that they're not routine. I would imagine that many of you don't routinely use diodes, TLDs or transit dosimetry to check the dose that you're delivering to your patients, and there's probably good reasons for that, which we'll come back to later. Another reason why we might want to check the dose that we're delivering is that we are working in a an increasingly litigious society. Although there's no statutory requirement for us to undertake in vivo dosimetry, in some European countries there is. And so we might want to at least ensure that we can demonstrate that we're delivering what we say we're delivering. Also, if we collect data from our in vivo dosimetry program, we can learn a lot about what we're doing with our radiotherapy, and we can learn where the weaknesses are and how we can improve them. See, these are all important aspects of an overall improvement strategy. But most importantly, remember that dosimetric errors can and do occur. So where do they occur? Well, equipment might be calibrated either incorrectly, or we know that there's some scope. So when you do daily checks, you know that the outputs of the machines have got to be within plus or minus 2% of expected. So there's some small error, potentially, in the delivery of radiotherapy there. How we acquire patient data. The fact that we base our planning on CT simulation, which is a snapshot in time, and isn't necessarily we might get both external and internal contours that aren't a true accurate representation of the patient on the day that they're treated. There might be some difference. So there might be some errors in the acquisition of patient data. CT, MR, we know that MR has some geometric uncertainties. So all these might contribute to some uncertainty in the acquisition of patient data that we base our planning on. And if we then transfer that through to the treatment, there might be some dosimetric uncertainty in the delivery of that radiotherapy. How we compute our dose distribution, we know that there isn't a perfect dose distribution that's produced by the treatment planning system algorithms. Some are better than others. Monte Carlo calculations are better than pencil beam calculations. We know that, but we don't always base our dose distributions on the best planning algorithm. So there's some uncertainties in what we see. We can't assume that what we see on the plan is what's going on in the patient. Data is transferred between planning and treatment, and again there could be some uncertainties there. There shouldn't be, but sometimes these can happen, and that's why we try and minimise human error in this. Also, in relation to the next point, why we've moved away from manual dose calculations, monitor unit calculations, take away all those human errors within that process. And then there's all sorts of other patient-related factors. We are blobs of organic matter, we move about, organs move about, we breathe, there's external contour change on a day-to-day basis, there's some inhomogeneities that might not be perfectly accounted for in the computation of dose distribution, patients move, we make small errors in how we set up patients. These all together contribute to some dosimetric errors, and we need to minimise the impact of those. You can add all these up, and generally what we'd expect to see is that in most cases a dose uncertainty in the region of plus or minus 3% between what we plan and what actually goes on. Okay. So how can we check the dose that's been delivered? So what we have are two options really. We can have point dosimeters, or we can use something called transit dosimetry. So point dosimeters are, as we can see at the top here, semiconductor diodes. We can have things called MOSFETs, which stands for metal oxide silicon field effect transistors. I'll repeat that, metal oxide silicon field effect transistors. These aren't widely used. Semiconductor diodes are. Or we can use thermoluminescent dosimeters. You can see here, these are in their little plastic wrappings, and at the bottom, the tiny little TLD chips that you can see. We can use any of these to assess the dose at a particular point in our field. Or we can do what we call transit dosimetry, which is exploits the EPIDs on our LINACs, which give us an indication of dose distribution that's transmitted through the patient. Now what I'll do is I'll look at these in a bit more detail in turn, and we'll start with TLDs, then we'll look at semiconductor diodes, and then we'll move on to transit dosimetry. So, TLDs, thermoluminescent dosimeters. The most common types of these in radiotherapy are lithium fluoride with an added impurity. That's usually magnesium or titanium, small amounts of magnesium added to the lithium fluoride. I won't repeat what you should have already done on how these things work, but just as a quick reminder, what you can see on this slide is the energy banding within a TLD. So the green represents the valence band. That's the energy level at which electrons are bound within the crystalline structure. The blue level represents the conduction band, i.e. the level at which free electrons can contribute to conduction. And then there's an energy gap between them, which I've called the forbidden zone here. Don't worry about that too much. This energy gap is actually where these impurities lie. So the energy level of these impurities lies between the valence band and the conduction band for lithium fluoride. So what happens when you irradiate these, you can see the little radiation beam coming in, is it excites the electrons, they get ionized, they jump into the conduction band, and then they want to fall back into that bound state in the valence band. They get caught in the traps that are provided by the impurities within there, and they get stuck there. Afterwards, what we can do is heat these up. That's why they're called thermoluminescent dosimeters. So that's the thermo bit. As they're heated up, it gives enough energy to these trapped electrons, such that they can be released back into the valence band, and the energy level difference between those traps and the valence band is equal to energy in the electromagnetic spectrum, the visible light part of the electromagnetic spectrum. So they give off light. So essentially, the number of trapped electrons is proportional to the absorbed dose within the TLD. You heat them up, they give off light, and the amount of light that's given off is proportional to the number of electrons, which is proportional to the absorbed dose. Nice and straightforward. Okay, so what about pros and cons of these? Well, it's fairly cheap. Actual TLDs themselves are really cheap, but you've got to then go ahead and reuse them. So they are reusable. And to do that, you need to heat them up to a high temperature over a long period of time to anneal them, and then they can be reused. That's actually quite a costly process in terms of the ovens that you need for that. So the reading out of these is automated, fairly straightforward. They've got a similar atomic number to soft tissue, and a similar electron density, which means that the dose that we read in them is the same as the dose that we'd expect to see in soft tissue. And they're very small, so we can position them quite reproducibly where we want to. There are numbers of disadvantages though. They are affected by things like grease, and they need careful handling. So they have to be handled by vacuum tweezers. That's why they're in those little plastic packets, if you've seen these being used. Any grease, anything on there will affect how accurately they can read the dose. The most important disadvantage is the lack of an immediate readout. So you put one of these dosimeters on a patient, you deliver the radiotherapy, you send the TLD back to physics, they do the readout, they send the information back to you on the treatment set, and you go, oh, that's way out. That shouldn't be like that. What can you do? Can you go and examine the setup and try and work out what went wrong? No, because the patient's gone home. It's too late. All you can do is repeat the measurement. What you need with in vivo dosimetry is an immediate readout, and TLDs don't give that to you. They can be useful for out-of-beam measurements, so for critical organ dose measurements. So you can position them close to the eye, for example, to assess or to estimate the dose to the lens of the eye for some head and neck patients. But other than that, they're not really used widely now in vivo dosimetry. More commonly, we use semiconductor diodes for point dose measurements. Remember, we're still talking about point dose measurements here. So many of you, I hope, will have seen these in practice. This is what they look like. They're colour-coded according to the energy range in which they should be used in. So as far as I recall, green is the lower energy band, so you use those in the sort of 4 to 8 MV. I can't remember the ones, I can't remember which one it is, but some of these other ones are used for higher energy ranges. And it's important, I'll explain why, it's important that you use these in the correct energy range. You can't just choose a colour you like, you need to choose the one that corresponds to the energy of the beam that you're assessing. So all the colour-coded ones on here are for different energies. The little black droplet one is to measure out-of-beam measurements, so critical organ doses. And the little grey one there is for electron beam measurements, if you wanted to do that. This one is for brachytherapy measurements, the long probe thing there. How they're used, very simple. You can see here, it's just taped onto the central axis of the beam, and this cable here connects to an electrometer, and it gives you an automatic readout of the dose as it's being delivered, and then you can, if it's out of a specified tolerance, more on that later, you can then decide what to do. You can go in, investigate what went wrong. In this case, it's quite likely that this will spring away because it's on these pubes here, move closer to the source of radiation and give you a higher dose than expected. And you think, oh, that's not right, wonder what's gone on. You go in, you find out that's what's happened, the tapes come off, it's moved closer to the source and has ended up with a higher than expected dose. And you can go, well, that's absolutely fine. There's obviously, it's an error in dose measurement, not in dose delivery. Okay, so let's move on to how these work. And it's all based around the physics that occurs around a p-n junction. So what we've got with any semiconductor diode are two bits of silicon. So what you can see on here is there's two bits of here that are stuck together. Excuse me. On the left hand side you've got a bit of N-type silicon that is doped with something from group 5 of the periodic table. So silicon's in group 4, it's doped with a group 5 material, typically phosphorus. And what that does is, and the energy level of those you can see represented by these dots here. And because it's in group 5, that donates electrons to the lattice. Now these electrons are free to move around. They're in the conduction band, that blue part you can see here. That's bonded to a much thicker bit of P-type silicon. Remember, silicon in group 4, that's doped with a material boron from group 3. And again, these boron ions here are fixed in that crystalline lattice, close to, the energy level is close to the valence band. And so they take an electron from the valence band, leaving these free holes here, which are free to take part in conduction. So you stick these two bits together, and these free electrons can cross over this boundary and start to cancel out the holes. So the electrons and holes wander across, cancel each other out, and they leave this area, and that carries on until you end up with a sort of a barrier itself, in that the electrons, they start to cancel each other out until they start to encounter a drift current the other way. They're repelled back by the negative ions that are left. Okay, so the phosphorus ions are left here and they're repelled back. These holes, if you like, are repelled back by the boron ions that are left here. So we end up with a region called the depletion region with no charge. So we've, on one side we've got an excess of electrons, on the other side we've got an excess of holes, and a region here that you can see on here called the depletion region, where there's no charge. Now what happens is that this bit, depletion region, becomes our detector volume. So you irradiate this, and as the radiation comes in, it causes ion pairs to be produced, so electron hole pairs to be produced in this depletion region. So these charge carriers are quickly swept across this potential difference. Remember, you've got a potential difference here of about 0.4 volts because you've got electrons on one side, holes on the other, and they're prevented from mixing any further by these ions within here. So electron hole pairs produced, quickly swept across this potential difference, and if you connect either side of this to an electrometer, it creates a current, and the current that's produced is going to be proportional to the number of electron hole pairs produced, i.e. the absorbed dose within this detector volume. So our semiconductor diode becomes a solid state detector. We connect it either end to an electrometer, measure the current, and then we can calibrate that to show us the dose. Now that's oversimplified a little bit, but it gives you enough of a reminder from stuff you've done in year 1. So the advantage of diodes over TLDs is that it provides us with a much simpler way of determining the dose. So it's much simpler instrumentation. All we've got is that business end that we stick to the patient, a cable connected to an electrometer, and it gives us a live readout, and that's the biggest advantage. We have an instant readout. It tells us what the dose is, we can compare that to an expected dose, and we can investigate if there's an error. If outside of a predetermined tolerance, we can go in and find out what's going on. We can determine whether it's an error in measurement or an error in dose delivery. So that's exactly what we want. They're very sensitive. They're so sensitive that if we wanted to, we could detect individual pulses of the LINAC. They give us a linear response to dose that TLDs don't. Above about 1.3 gray, TLDs exhibit what's called a supralinear response. So you get a shoulder, and it doesn't, we have to then, well, we don't have a good estimate of what the actual dose is in there. Now, if we're delivering higher doses per fraction, we don't have to worry about that with diodes. We get a linear response. Far more robust. We don't have to worry about grease and stuff affecting the accuracy of the dose that we measure. Having said that, you can't really go sort of standing on them or throwing them about. So the actual detectors themselves are slightly sensitive, but much more robust than TLDs. They're a bit more expensive, obviously, but overall the cost of the system is cheaper because it requires less man hours. So a fairly cheap system in comparison to using TLDs. And because of the design of them, they give us a determination of the dose at Dmax. So it tells us the applied dose. So if we stick a diode on the central axis and measure the dose, it gives us the applied dose that's been delivered to that patient. And we can compare that with the applied dose that we're expecting it to be. They're not without disadvantages though, of course. They're not perfect. The main one, of course, is that they only give us a point dose measurement. So for intensity modulation radiotherapy, that's no point. It's useless. You know, what we need is assessment there of dose fluence across the whole field. This only gives us a point dose. Fine for simple techniques. Okay, it's great for simple techniques. They do require connection cables, which isn't really a problem. But in the old days, they used to trail across the floor, go through a duct in the wall into the area outside the room, and it'd be easy to fix them to the patient and then trip up over them on the way out. Most of them nowadays, as you'll see, are connected via ceiling mounts. Also, we need to be careful that their sensitivity varies with a number of things. And so we need to think about how we calibrate them. So firstly, their sensitivity varies with energy. You can only use diodes in the energy range in which they're expected to be used. They also lose sensitivity over time. So as you use these more and more, their sensitivity decreases. So you have to calibrate them every month or so to allow for that effective radiation dose. They're also sensitive to temperature, which is important because we put these on the skin surface. Skin surface has an average temperature of about 31 degrees. Room temperature, as you know, is about 21 degrees. So there's a 10-degree difference there. If we didn't account for that, that will give us an error in measurement in the region of about 3%, between 3 and 5%, which might not sound a lot, but that can be significant when what we're trying to do is keep our tolerances to a reasonable amount. So that's important. Now what we can do, as we can see here, is we can calibrate them at skin temperature, average skin temperature, or we can just use a bigger tolerance. And so this was filled with hot water, wait for it to get the temperature gauge on the top, little thermometers, and then when it's at the correct skin temperature, calibrate them, measure the dose that's being delivered. Finally on here, beam perturbation. So what we've got in these little diodes are build-up caps, little bits of metal. We'll see this on the next slide, I think, or the slide after. So actually they act like little shields, and you can see that on this dose profile here. So where the diode has been positioned underneath the central axis, there's a reduction in dose because it's going to attenuate the beam. Now that's not a problem if you only use these periodically. So you can't use these on a day-to-day basis, otherwise we would underdose part of the whatever it is that we're trying to treat. So we can't do that. So that's something to consider as well. We're going to reduce the dose by about 5% underneath the diode. They all look like this in cross section. They're all 7mm from front to back. And this is the business end, number one. The diode, it's only tiny. That's covered in some epoxy resin and then a metal build-up cap made of stainless steel. That's number 3. So the stainless steel build-up cap, that varies in thickness according to the energy range that it's intended to be used in. So we're measuring the radiation beams coming in here, and we're measuring the dose at Dmax. There's a cable, little connectors either end of the diode, as I've already explained, which take it to the electrometer through the cable number 6. So they all look like that in cross section. It's the thickness of this steel build-up cap that varies according to the energy range they're meant to be used in. Here's the ceiling mount. That's typically, if you've got this in your department, you'll be used to seeing this. And so these like kind of little inertia cables here, you can pull them down, fix it to the patient, and you don't have to worry about tripping up over them. And the cables go out of the room attached to an electrometer that looks like this, and you will see the dose accumulating on these little readouts as you deliver the radiotherapy. So, it gives you the dose, so what do you do with this? Well, the first thing to remember is that you're measuring a point dose. And normally you're measuring the dose along the central axis, so you're comparing the applied dose that you're delivering with an expected applied dose. So what sort of tolerance level should we be employing? What's acceptable? does it have to be more than 3% different, 5% different, 10% different? How much? Okay, and this is where there's some uncertainty. Most departments use a tolerance level of 5%, but that's not necessarily always the best idea. And what we need to consider is how accurately we can estimate the expected dose. So based on the acquisition of patient data and the calculation of dose distribution and the calculation of applied dose. That's the first thing we need to consider. Secondly, we need to consider, are there any measurement problems posed by the clinical situation? Is there a high angle of incidence? So for example, is it an oblique beam for a breast treatment or a head and neck treatment? Is it tricky that the diode might spring up or down according to body hair? Is the diode positioned in a high dose gradient? All of these things can affect how accurately we can measure the dose. So there's going to be some degree of uncertainty in the measurement process. Now you might think instinctively and intuitively that actually it's better to have smaller tolerances because that means we're delivering a more accurate treatment. But in general practice, the accuracy that we can achieve is between 3 and 4%. In other words, if we have a tolerance dose of 3%, we're going to see a heck of a lot of measurements outside of tolerance, and all that's down to is errors in dose measurement, uncertainty in dose measurement, and nothing else. So having a smaller tolerance excuse me, is actually a bad idea. And so paradoxically, it's better to have a larger tolerance or action level, because then if it reaches that tolerance level, it's likely to be something that you're able to identify. It's going to probably be an error in dose measurement. The diode will have moved, or the patient's moved. If the patient's moved, it's an error in dose delivery. But most of the time, it's an error in dose measurement. But by having larger tolerances, you're better able to identify errors in dose measurement and dose delivery, and not get overawed by high numbers of readings outside of tolerance where you can't find anything wrong. Now that sounds weird, and perhaps that's something we can address in the Q&A session in the follow-up webinar for this. Okay, so in this next part of the session, we're going to move on to transit dosimetry or portal dosimetry. And the question we need to ask ourselves here is, we've got something on our Linacs that allow us to do this without any significant additional cost and time. And of course, it's our amorphous silicon EPID panel that we can use. So let's have a look at that. So remember so far, point dose measurements with diodes, great. Okay, can be really useful for simple techniques. It's got some problems, but it can give us confidence in what we're doing with these more straightforward techniques. With many of the techniques that we use now, with IMRT, Sabre and so on, if we want to verify the dose that we deliver, then we can't use diodes. We have to use some sort of transit or portal dosimetry. So let's explore that in a bit more detail. Well, this working from home means we get to spend much more time with our pets. I'm joining Wilma here in her favourite spot, looking out the window, waiting to bark. You'll hear at some point. What do you think, Wilma? Diodes got a place in radiotherapy? Point dose only? Not worth it now, is it really? IMRT? Transit dosimetry? Yeah, that's what we should be doing. Set up for that? Everyone doing it? No. They're Wilma's thoughts anyway. Anyway, let's crack on. Okay, so you all know that although most of you use cone beam CT now for geometric verification, you know that in the good old days that amorphous silicon detectors, or EPIDs, were used for geometric verification. They showed us anatomy in a blurry way, but actually what they're providing us with are dose intensity maps. So when we look at these, actually what we're seeing is where it's black is where there's more radiation getting through to the image intensifier, where it's white, there's less getting through. And so any shades of grey represent different doses. Now the good thing about amorphous silicon intensifiers for these is that they provide a very stable response. They do require calibration, and you can see that at the bottom. They need special calibration for transit dosimetry. It's not simply a case of being able to look at an EPID and go and actually, I don't know, use some form of device to measure the degree of blackness and convert that automatically into dose. That's essentially what happens, but it's a bit more complicated than that. We don't have to go into all the physics, but we've got a pretty linear relationship with dose rate and dose and what we see on the EPID in terms of its response. So the beauty of this is we get a full fluence map, okay? And in general, what we can do is we can produce an expected dose map, we can produce a measured dose map, and we can compare them. That is the basis of what's happening. Here we go. So this is essentially the oversimplified process. So what we produce from our planning system is something called a predicted portal dose image. So there's some software within the treatment planning system that, based on the dose distribution, provides us with a predicted portal dose image for a particular field, okay, or combination of fields. So we can see that on here. This is our predicted portal dose image, and it's a color map, a color dose map. What we then do is, with our calibrated EPID, we convert the image that we see into an actual portal dose image. So this is a portal dose image, and this is a predicted portal dose image, so predicted versus actual, and we can compare them. We can overlay them and use software to produce what we call a gamma evaluation map. Okay, and we can see that here. So we can see that where there are areas appearing towards red is where there is some discrepancy between the predicted and the portal dose image. Okay. So a little bit more about gamma evaluation on the next couple of slides, but essentially that's the basic process. Predicted portal dose image, an actual portal dose image. We require software for both. We can then compare both with using something called a gamma evaluation to give us essentially a map and some numbers that show us where there's similarity and differences. So you don't need to worry about how it's calculated, okay? That's a relief for you, I'm sure. But yeah, it's just a method for quantitatively comparing two fluence maps, a predicted map and an actual map. Okay. Now it's one number that you get for any point, and it incorporates two things: a difference in dose and a distance to agreement into one single measure. So if you want to know a little bit more about that, go to this paper here from 1998. So if we go back to the previous slide, you'll see here, this is our gamma evaluation, and what we're using here is 3% and 3 millimeters. So anywhere where it's greater than 1 is considered to be a more significant discrepancy. That's based on this threshold of 3% and 3 millimeters. So when we compare the points, they need to be within 3% of the dose, and that's based on differences of 3 millimeters from each other. Clearly, the higher they are, so if that was 5% and 5 millimeters, this would all be blue. Okay, there would be little or no discrepancy. If we use 2% and 2 millimeters, a lot more of this would appear towards the red. There would be differences. So it's basically our tolerance that we're applying, and most people use this 3% and 3 millimeters. So again, you don't need to worry too much, okay? Just remember that the gamma criteria are indicated as a percentage of dose difference and a specified difference in millimeters. So it's a dose difference and a distance to agreement. And as I've said, typically 3% and 3 millimeters, but it can vary. Okay, so in summary then, with EPIDs, it's a great way of ultimately verifying and quantifying the dose and verifying a dose fluence map that we're delivering. So it's great for IMRT. The equipment that we need for it is mostly already available, although there's some additional software requirements that's required for the treatment planning system and for our EPID system. So that's the only additional cost associated with this, plus the additional time that's required for somebody to assess the gamma evaluation and make a judgment about what to do. So protocols are still being developed in relation to this. So when do we correct? When do we replan? What gamma criteria do we use? Okay, so hopefully you found that useful. There is going to be a Q&A session with an online webinar. Please turn up to that. If you've got any questions about this presentation or anything else you need to know about in vivo dosimetry, I'm there to help you out. Okay, thanks for listening. Right, so Wilma hopes that you found that useful and invites you to the Q&A session. Don't forget. Okay, that's Thursday. What time? 2 o'clock, something like that. It's on the Blackboard side. Okay, bye.